Okay, we have several properties of vector spaces. We're just going to look at a couple of examples in addition to ones we looked at last time and try to get a handle on how we prove some of these properties. We have closure, commutativity of addition, associativity of addition, zero vector, additive inverse, etc., etc. Just looking mainly at these five. We consider the set of integers, the set that consists of all integers. So we represent that set by, the way we've represented it here. I'm not going to read it to you. This is a set of integers. Okay, so closure. That means if you add two integers, you get an integer. Well, that's certainly true. Commutativity of addition. Well, yeah, if you add two integers in one order, you get the same things if you add them in the other order, because addition of real numbers is commutative. Associativity, well, yeah, integers are real numbers, so if you add three of them, you can group them in any way you wish. So that's certainly true. The identity, our zero vector for addition on integers, that is the zero vector is the vector that could be added to any other to get that other vector. And clearly the zero vector would be the integer 0. 0 plus n equals n. And we should also say that n plus 0 equals n, but since the thing is commutative, that's implicit. But that really does kind of need to be stated. So 0 plus n is n, so 0 is a zero vector, and 0 is an integer, so the zero vector is in your vector space. It could be that you have a perfectly sensible zero vector that is not in the set. What if this was a set of odd numbers? Well, it wouldn't be closed under addition, would it? Because if you add two odd numbers, you get an even number. It would be commutative and associative, but it wouldn't be closed, so you would just kind of stop there, wouldn't you? But if it wasn't closed, well, you wouldn't have an identity in that set, because 0 would not be in the set of odd numbers. Okay. Additive inverse, well, if n is an integer, what do you add to n to get the zero vector, which is the number 0 in this case? Well, obviously, that would be negative n. So you have your additive inverse. Yep, so we got that. Now, we have all the others too, and you can easily verify all of them. You just have to be sure you understand what they're saying and write out carefully what the meaning of that particular property is for this set on the operation of addition. And I did mention closure under scalar multiplication. Actually, I said they all work out. This is a set of integers. They don't all work out. Okay. What about closure under scalar multiplication? Here's where you run into trouble. Let n be an integer, let c be a real number. Is c times n even an integer? No. Not necessarily. I mean, it could be. C could be another integer, but c could be any real number. C could be the square root of 17. You multiply the square root of 17 by just any integer, you're not going to get an integer. Okay? And that's going to be true pretty much if c is any irrational number, and that would be something you might want to think about. If c is any irrational number, you multiply it by an integer, you don't get an integer. You can't get an integer by multiplying an irrational number by an integer. Okay? Again, just proving that would be an interesting proof, but we can easily do this just by examples. So that's not so the set of integers is not a vector space. Okay, what about the set of singular 2 by 2 matrices? Okay, now first of all, what does singular mean? We should know by now, but these words, vocabulary is always a little bit of a challenge. It means it's non-invertible. It means it has zero determinant, several equivalent statements about singular matrices. So let's just test closure. Now, what I asked everybody to do is just see if you can write down two singular matrices that add up to a matrix that isn't singular. Well, a good, about half the class was able to do this in various ways. the most common was let the first matrix have zeros through the first row, so the first row is a row of zeros. Let the second matrix have a row of zeros, so that'd be the second row. Both of these are singular, but if you add them, you get this, and that's certainly not singular. So we immediately prove that the set of singular 2 by 2 matrices is not a vector space, because if you add two of them, you don't necessarily get one. Okay. How about this? And I started to write this down, writing down two problems at once, but it's a set of ordered pairs x, x plus 1, where x is a real number. Okay? Is this closed? So again, we look at closure first. That is often where things fail. Okay, so closure is always a really good one to look at. So let's say we have two numbers of this form. And let's call the first one, say the first component is x1 here, and the first component of your second number is x2. Well, if the first component, the x component of your first ordered pair is x1, then since it has this form, the second component is x1 plus 1. And if the first component of the second vector is x2, then its second component has to be x2 plus 1. Now, what do we get when we add these? Well, we get x1 plus x2 for our first component, and x1 plus 1, x2 plus 1 for our second component. And when we simplify the second component, we have x1 plus x1 plus 2. Now, the form of, and I can, just to emphasize this, I can put parentheses around this x1 plus x2 and around this x1 plus x2 just to show that, okay, here's the first component and here's the second component. Okay, the second component has this, which is the first component, but then we're adding 2. Well, that's not of the form x plus 1. If x is x1 plus x2, then x plus 1 is x1 plus x2 plus 1, not x1 plus x2 plus 2. The form of this number then is x plus 2, not x plus 1, so this set is not closed.